Here, let me pull it up.
Okay.
Alright, just variation is what we're currently working on right now.
Okay. Is it
And
the stuff you can formalize?
yeah, it's easily verbalizable.
Okay.
It's just the like structure of the problems that kind of confuse me.
Okay.
Okay, so here's an example. If y varies directly as x squared and y equals 25, when x equals 3, find x when y equals 100.
All right. The two things you have to know is what direct and inverse means. If y varies directly with x, I can write it like that.
Uh-huh.
If y varies inversely with x, I can write it like that. And k is a constant that you're going to have to solve for. And every one of these problems, the first step is to solve for k. Okay? This is the general equation for y varying directly with x. This is the general equation for y varying inversely with x. Well, they said direct, so we're dealing with this one. And now they give you specifics. They say when y is 25, x is 3. Well, that's going to allow us to solve for k for this particular problem. Plug in 25 equals k times 3. K equals 25 divided by 3. And now the specific equation for that problem is this.
Okay.
And now the last part of the question was what? What is y when x is something?
100.
So when x is 100, y is 25 thirds times 100.
Okay, that makes sense.
It did say what is y when x is 100?
Yeah.
Yeah. So you always start out with the general, and then you find the specific, which I've circled, and then you can use the specific equation to figure out any y given any x.
Okay.
Okay. What else?
Okay, and then there's this one that really caught my attention.
Okay.
Let's find it here. All right. To estimate the number of flamingos at the Lake Manyara flock, the Kenyan Wildlife Service has banded 600 birds. At a later time, they caught 1,000 birds and found that 48 were banded. And about how large is the entire flock? For this problem, use a proportion.
All right. Let me make sure I understand it. They started with 600 birds?
They banded 600 birds. And then at a later time, they caught 1,000 birds and found that 48 were banded. About how large?
How many were banded originally?
600.
Ah, so 600 banded. Given some population of birds, right?
Uh-huh.
That ratio probably stays the same. And at a later time, they found how many? 45 banded?
48.
And they want to know...
Out of 1,000 birds.
Ah.
So would you just cross multiply?
Yeah. In other words, we have a proportion here with only one variable.
Mm-hmm.
So we can figure out what x is, and that would be the total number of bird population that they started with. That they only banded 600. But so x here, 48x is going to be equal to 6 with 5 zeros. And x is going to be that number divided by 48.
Okay.
And do you have a calculator in front of you?
Yeah, I can get it.
It's always good to come up with a number just to see if it makes sense.
Yeah. 12,500.
So, if we go back into this, does this make sense? In other words, we banded that percentage of the 12,500 birds, and that percentage is the same as that percentage.
Okay.
And what this allows them to do, notice, is they didn't know how many birds they started with. Is all they did was they banded 600 birds that they found.
Uh-huh.
And at a later date, when they find 48 banded birds out of 1,000, well, that should be the same proportion as 600 to however many birds there were to begin with. And 12,500 makes sense. 12,500 is more than 10 times 1,000, and 600 is more than 10 times 48.
All right. That makes sense to me.
Okay.
Okay, and we were, hold on one second.
Back to that original problem where you were doing direct and inverse.
Yeah.
There's a good one that says the force of gravity between two objects is directly proportional to the mass of object 1 times the mass of object 2 divided by the square of their distance.
Uh-huh.
Well, another way I could say that would be that the force is directly proportional to the product of the masses, but inversely proportional to the square of the distance between the masses.
Uh-huh.
And that is one of the most fundamental laws in the universe. Newton came up with that when he figured out what is the force that affects two planets. Well, he figured out a K, and there is a number for K, but the essence of the problem is that it's some number K times the product of the two masses divided by the distance between them. But when we're dividing, that's the same thing as saying F varies inversely with the square of R.
Oh, yeah?
If I were to just tell you that alone, and I said F varies inversely with the square of R, that's the way I would write it.
Okay.
Okay? And then, of course, if they told us the mass of two planets and the distance between the two planets, we could figure out K if we knew the force, the gravitational force between those two planets. All right, what else do you got?
Okay. So, we were working on a... Okay. We were working on a... I'm trying to find the name of it. Oh, graphing rational equations.
Okay. Graphing rational functions. And a rational function usually has a numerator and a denominator. In other words, something like this would be a rational function.
Yeah, that's actually an example. Like, how would you find the vertical asymptote of that?
The vertical asymptote always comes when the denominator is equal to 0. So what makes the denominator 0?
Positive 2.
Okay, so I'll start the graph by drawing the vertical asymptote in at 2. What's the horizontal asymptote?
I don't know how you find that either.
It's the ratio of the coefficients of the highest. If the x is the same degree in top and bottom, then the horizontal asymptote comes at the ratio of their coefficients. In other words, 1.
Huh.
If that was a 3x plus 1, then the horizontal asymptote would be at 3. If that was 3x and that was 2x, the horizontal asymptote would be at 3/2.
Oh, so it's just the...
Just the ratio of those coefficients. But that's only if these are the same power. If I make that 3x squared, now there is no horizontal asymptote. Or if I put the square in the denominator, now the horizontal asymptote is 0. In other words, if the highest degree in the denominator is greater than the highest degree in the numerator, the horizontal asymptote is always 0.
And if it's higher in the numerator, then it's there is none.
Well, then you actually have, if it's exactly 1 higher like that, the first step is to do the division.
So you basically just have a linear equation then.
Well, you produce an oblique asymptote. In other words, if I do that division, the linear factor that comes out is the equation of the oblique asymptote. That might look like that. And there wouldn't be a horizontal asymptote. So I'd be looking at something like that. And the graph might look like this. So you can have oblique asymptotes. Have you covered oblique asymptotes yet?
No, I haven't.
Okay, well let's ignore those then. I don't want to really introduce something you haven't covered yet. So you're not going to get this situation where the numerator is exactly 1 degree higher than the denominator, because that necessarily gives you an oblique asymptote. The only 2 situations they're going to give you is where they're equal. Even if that was x cubed and that's x cubed, horizontal asymptote is at 3/2.
Okay.
So, and it doesn't matter what else. In other words, if I have 3x cubed plus 17x squared minus 100, all divided by 2x cubed minus 1000x squared plus 1,000,000. The only thing that matters for horizontal asymptotes are these 2 terms. You can forget everything else. It's like end behavior. The end behavior is only governed by the highest degree term of that polynomial, which in this case would be the x cubed term, top and bottom, and their ratio is 3/2.
Okay, well that makes sense.
What other problems do you have more specific rather than me making some up? But not that I mind, but without knowing exactly what you've been taught, it's a little hard to make up the right problems.
Okay, so here's an example of a problem. So that you have to graph the function and then state the domain and range.
Okay.
And here it's y equals 1 over x minus 7
That it?
plus 3. And then plus 3.
Okay. First thing we notice is that there is an x value that causes division by 0. That gives us a vertical asymptote. At where?
7.
Where's the horizontal asymptote?
Wouldn't it just be at 0?
Well, it would be at 0 if that's the only thing that matters. But this plus 3 is a vertical shift up 3 units. And that moves your horizontal asymptote.
And that's only ever a vertical shift. It's never a horizontal shift.
Correct.
Okay.
So there's our vertical asymptote now. And now we have a grid with which to plot. And typically, these are hyperbolic in nature, all of them. Rational quotients tend to be hyperbolic in nature. Okay? Hyperbolic functions generally plot like this.
Mm-hmm.
Sometimes, if there's a negative sign involved, instead of in the first and third quadrant, it might be in the second and fourth quadrant instead. And if you want to know which, plug in an x value greater than 7.
Or?
Am I in the right quadrant, the way I've graphed it?
Yeah.
Yeah, because any value greater than 7 gives you a fraction plus 3, so it's got to be above the dotted line 3, and we're in the right spot. In other words, my only question when I went to graph it was whether it was the way I've drawn it, or could it have been like this?
If you had negative 1x minus 1 over x minus 7 with that.
You got it, exactly. Now, you can't always tell by just the negative sign. If it's a complicated looking function, then the best way to tell is pick a point to the right of your vertical asymptote and figure out whether it falls above the y equal 3 or below y equal 3. Notice that if it was 1 over 7 minus x, instead of x minus 7, in other words, let's say it's 1 over 7 minus x plus 3. Now if I pick a number greater than 7 for x, that's negative. Which means that it would fall down here somewhere. So the best way to really determine which quadrant you're in is to plug in a number and make sure that it puts it in the right quadrant as to the way you think it is.
Okay.
Okay. Now, they wanted, so the red is proper, and they want the domain and range, right?
Yeah.
Well, if I look at my picture, what's the domain?
Would it be all real numbers except for 0? All real numbers except for 7?
Correct. All real numbers except for 7. And that's really, if they want to, have you had interval notation?
What's that?
Well, if I wanted to say, there's a few ways to express that. One, I can say x equals all reals except x not equal to 7. That's the one way to say the domain. The more precise way to say the domain would be an interval notation, which is it can be minus infinity to 7, can't be 7, in combination with 7 to plus infinity. So this is the more specific way to spell out domain. And notice I put parentheses around the 7 because it cannot be 7. If it could be 7, I would use a bracket.
Okay.
This is interval notation. If you haven't had it, no problem. We'll just read everything in this kind of notation.
Okay.
What's the range of this function?
Wouldn't it just be all real numbers, or no?
Can it ever be 3, according to my graph?
No.
And notice why it cannot be 3. The only way y could ever be 3 is if I can make that 0.
Then you can't.
You can't, because its numerator is 1. The only way you can make that 0 is if you have a 0 in the numerator. So it's impossible to make 1 over x minus 7 equal to 0. And if you can't make this part of it 0, then you can't make the whole thing 3. So there is no value of x that allows y to be 3.
Okay.
Okay? So the range, again, if you could say all real numbers except y equal 3.
Okay.
All right, what else?
Can we go over one more example?
Sure.
We have y equals 4. Actually, can I change it up? X plus 2 over x plus 3.
Yeah, now see, this isn't immediately obvious which quadrants I'm going to be in. Always start with your vertical and your horizontal asymptotes. Where's the vertical asymptote?
-3.
Where's the horizontal asymptote?
1.
Y equal 1.
Yeah.
Those asymptotes are equations of a line. So it's not technically correct to say at 1. It's the equation of that line is y equal 1. The equation of the vertical line is x equal minus 3. Okay?
Uh-huh.
Now, I suspect that it's this way, but to be honest, I'm not good at telling that just from that. I really need to plug in a value. Well, the value you want to plug in is to the right or left of the vertical asymptote. So pick a number and we'll be able to tell whether it's correct on the correct side of my asymptotes.
4.
Okay? When x is 4, what is y?
6/7.
Is that, have I drawn it correctly? In other words, 4 is way out here. And you told me that when x is 4, y is 6/7. Is that spot right?
I think so.
No? Well, that line is above 1.
So it'd have to be the other way around.
Exactly. In other words, it has to be a hyperbolic function that looks like this, and not the way I originally drew it. In other words, I call this the second and fourth quadrant, even though that's not technically correct. As long as there's only 4 quadrants, you can do that. But some of these have 2 vertical asymptotes, and then there's like 6 quadrants, 3 on top and 3 on the bottom. But if there are only 4 quadrants, it usually is in first and third or second and fourth. And like I said, it's not intuitively obvious as to which one it is when you look at that. I don't see any minus signs. So I can't tell by the absence of minus signs. I just have to pick a number. And notice that if I pick the number 0, y would be 2/3. Well, there's 0. Y is certainly not above 1. So maybe I drew it not exactly right, because when y is 0, it's got to go through that point right there, but close enough. like that.
Mm-hmm.
The whole key is just to figure out whether you're in that first or the fourth quadrant when you pick a number.
Okay.
And notice that if I pick -2, that's 0. Well, here's -2 and there's y equals 0. So that's further confirmation that I'm in the right quadrant.
Uh-huh.
Now, there's one slight difference. If I have that rational quotient, I'm going to have to run here pretty quick just because I have a 630. This graphs like this in the first and second quadrant because it's squared. In other words, y is never negative. No matter if x is positive or negative, y is always positive. So this graphs in quadrants 1 and 2. So you got to be a little careful if you see terms that are squared. It's not always first and third, second and fourth.
Uh-huh.
But most of the ones you'll be looking at will be first and third, second and fourth. That's second and fourth.
Okay.
Okay? All right, Jake. Well, good luck. Glad to hear you're doing well.
Thanks.
Talk to you next
All right.
time.
Thanks.
Bye-bye.